Hello guys, welcome back to my channel, and today I'm going to do an integral that I have done in the past, but I'm going to use a different method. So I'm going to be integrating sine of x over x from 0 to infinity, but this time instead of using the Leibniz technique or the Leibniz rule or the Feynman technique, I'll be using the method of using Laplace transforms. So let's get to it. So we have our problem, let's call it I, being defined as the integral from 0 to infinity of sine of x over x dx. And as I said, instead of using the Leibniz rule or the Feynman technique, we'll be using Laplace transforms like we did in our previous video. So if you haven't seen that yet, I have provided a card right about now. You can click on that and watch that video before seeing this, because I have explained Laplace transforms briefly, what they are in that previous video. So we have our I now. Let's define what the Laplace transform is. So the Laplace transform of a function of t, f of t, let's say, is going to be the integral from 0 to infinity of e raised to negative st times f of t dt, and this will give us an output function, let's call it capital F, which is a function of s. But notice that we have to have a function of t for the Laplace transform to be applied to it, and we don't have a t here, right, in our original problem. So let's parameterize it like we usually do for our Leibniz rule, but in this case we're not going to be parameterizing it as e raised to negative tx. Instead we'll be adding the t inside with the sign divided by x dx. And if you remember, if you've seen that that video of integrating sine x over x using Leibniz rule, you might remember me explaining why this sort of parameterization doesn't work in that case. However, now we have to rely on that sort of parameterization to get our job done. So now we have a function of t, right? Let's take the Laplace transform on both sides. So we have the Laplace transform of I of t being equal to the Laplace transform of this integral from 0 to infinity of sine of tx divided by x dx. And this is going to be, let's use the definition of the Laplace transform. We have integral from 0 to infinity of e raised to negative st, but instead of the function f of t we have this integral, right? The integral from 0 to infinity of sine of tx divided by x dx and an external dt. So this here we have a nested integral now. So what do we do after this? So like we did in our previous video, I would like to assume uniform convergence again. So I'm assuming uniform convergence. And why do we assume that? Because that enables us to interchange these integrals. So the external integral can be taken inside and the internal one can be brought outside. So then we obtain the Laplace transform of I of t being equal to, now the dt integral was outside and the dx one was inside. So let's take the dx outside now. Since the upper and lower bounds are same, We don't need to worry about that. We have uh, integral from 0 to infinity of e raised to negative st times sine of tx divided by x. But as I said, let's interchange them. So dt and dx now instead of dx and dt. So now notice inside we have integration with respect to t. Now all those terms that don't have a t are a constant with respect to t, right? So x is a constant, so it can be brought outside over here. But you can't take that outside this integral because we're integrating with respect to x there. So we have integral from 0 to infinity of 1 over x, and inside we have an integral from 0 to infinity of e raised to negative st times the sine of tx dt dx. Now notice that we had a dt here, that's why, and all these terms also have a t, so they can't be taken outside this internal integral. And what does this become? This is the integral from 0 to infinity of 1 over x times, well, notice that this is nothing but the Laplace transform of sine of tx, right? And a dx. And notice that we have a function of t. So our Laplace transform makes sense. And we don't need to luckily parameterize anything further. So unlike my previous video, I'm not just going to plug the formula for the Laplace transform of sine of tx. I'm actually going to show you manually what this finally equates to. So I'm going to do that on a fresh page. So we have the Laplace transform of the sine of tx. Let's remember our Laplace transform formula. It was the integral from 0 to infinity of e raised to negative st times f of t. What's f of t here? Sine of tx integrated with respect to t. Well, we have an exponential function and a trigonometric function being multiplied together. So a very good strategy would be to perform integration by parts. But a greater observation still is knowing what to integrate and what to differentiate. So knowing the properties of the exponential function, I suggest we should integrate this as we always do and differentiate this. So integrating that, we have negative 1 over s, which can be taken out as common, and the negative to compensate for the antiderivative of e raised to negative st. We have e raised to negative st times sine of tx as it is from t equals infinity to t equals 0. We have to evaluate this function at both the upper and lower bounds, minus integral from 0 to infinity of e raised to negative st times cosine of tx, but since it's an integration with respect to t, the x can be taken out as constant. Chain rule when we're differentiating. Sine of tx with respect to t, x is a constant which will come out. It's just the chain rule being applied properly. So we finally obtain negative e raised to negative st times sine of tx divided by s, and we have to evaluate that at the upper and the lower bounds. So first let's do it at infinity. So limit as t approaches infinity, minus of minus will be a plus, limit as t approaches 0 of e raised to negative st times sine of tx divided by s, and this is going to be minus minus plus x over s times the integral from 0 to infinity of e raised to negative st times cosine of tx dt. So as t goes to infinity, the sign of tx will just keep oscillating between -1 and +1, while this term e raised to negative st will blow up to 0, will decay to 0 actually. So this will go to 0, and when we have a 0, we have e raised to 0, which is 1, and sine of 0 times x, sine of 0 is 0, so even this term will go to 0. So we now have x over s times the integral from 0 to infinity of e raised to negative st times the cosine of tx dt. Looks like we have to apply integration by parts again. Therefore we obtain, let's take a negative out to compensate for the antiderivative of e raised to negative st, x over s times s squared, fresh s because of the antiderivative of this e raised to negative st, and we have e raised to negative st times cosine of tx evaluated from t equals infinity to t equals 0 minus integral from 0 to infinity of e raised to negative st times derivative of the cosine is negative sign, so negative negative positive sine of tx, and x is a constant, chain rule. So we have the Laplace transform of sine of tx being now equal to, so limit as t tends to infinity of negative x times e raised to negative st times the cosine of tx divided by s squared minus minus plus the limit as t goes to 0 of x times e raised to negative st times the cosine of t times x divided by s squared. And don't forget this other integral that we have with negative x squared over s squared times the integral from 0 to infinity of e raised to negative st times the sine of tx dt. So as t goes to infinity again, cosine, like the sign, is bounded between a -1 and 1, and e raised to negative infinity will decay to 0, so this term will go to 0. As t goes to 0, we have e raised to 0, which is 1, cosine of 0, that is also 1, so we have x over s squared because these other terms will go to 1. So we have x over s squared minus, and now notice what this is. This is again the Laplace transform of the sine of tx, right? So x squared over s squared times the Laplace transform of sine of tx, and this is just equal to the Laplace transform of sine of tx, right? So let's add this term on both sides. We obtain 1 plus x squared over s squared times the Laplace transform of sine of tx being equal to x over s squared. So just taking cross multiplying properly, s squared plus x squared divided by s squared times the Laplace transform of sine of tx is nothing but equal to x over s squared. S squared will cancel out proudly, and therefore now cross multiplying again, we have Laplace transform of sine of tx being equal to x over s squared plus x squared. And I had specified well before that the Laplace transform is always going to be another function, but it will be a function of s. Since we put input t, we'll get out of an output of a function of s. So nice, we have our Laplace transform of sine of tx. Let's plug that back into our original problem. So the Laplace transform of I of t is going to be the integral from 0 to infinity of 1 over x times, well, we know the value of the Laplace transform of sine of tx, we just calculated that. So that's going to be x over x squared plus s squared dx. And now look at the beautiful side of math. The x is cancelling out nicely. So essentially we got rid of this crazy part of the denominator that is actually hated during integration, because we always were finding ways to get rid of the denominator. Finally we got rid of that. So we have the integral from 0 to infinity of dx over x squared plus s squared, and we can just apply the inverse tangent formula of integration on this thing. So we have the Laplace transform of I of t now being equal to 1 over s times the inverse tangent of variable over s, so x over s, but since it's a definite integral we need to evaluate that from x equals infinity to x equals 0. So we can write this as the limit as x tends to infinity of 1 over s times the inverse tangent of x over s minus when we plug in 0, we have the inverse tangent of 0, which is 0. So this is going to finally evaluate to the Laplace transform of I of t will be the inverse, the limit as x approaches infinity of inverse tangent of x over s is basically going to tend to inverse tangent of infinity, which is pi over 2. So we have 1 over s times pi over 2. So we nicely obtained a small compact form for our Laplace transform of I of t. So last time we obtained the expression Laplace transform of I of t, our parameterized function, was equal to 1 over s times pi over 2. Now we need to get rid of this Laplace transform, right? Because we need I of t just alone. We don't need a Laplace or anything on that. So what we're going to do is we're going to take the inverse Laplace transform on both sides. So that's going to look like the inverse Laplace transform of the Laplace transform of I of t is now going to be the inverse Laplace transform of 1 over s times pi over 2. So inverse Laplace of the Laplace transform is just, they're going to mutually cancel each other off. So you just have an I of t simply. But one of the properties of the inverse Laplace transform is you can take a constant outside. So pi over 2 can be taken outside times the inverse Laplace transform of I of s. So I of t is now equal to, what's the inverse Laplace transform of I of s? So the real question you should be asking yourself is what function when applied the Laplace transform on gives 1 over s? And if you have your sheet of Laplace transform beside you, or if you know this, good for you, but the answer to this is 1. The Laplace transform of 1 is 1 over s. So pi over 2 times 1 is just pi over 2. So we obtain I of t expression for our generalized problem. But what is this I of t? I of t is nothing but integral from 0 to infinity of sine of tx divided by x dx. And how does that relate to I? What's I? I is integral from 0 to infinity of sine of x over x dx. Now notice that I of t when t equals 1 is nothing but our original I, the original problem that we actually need to solve for. But notice that there is no expression of t in our I of t form. So this means that I of t is a constant function which has a value of pi over 2 for all values of t. So I is, irrespective of whatever t you have, is always going to be pi over 2. So this is going to be pi over 2. So now notice that we had our I as integral from 0 to infinity of sine of x over x being equal to pi over 2. We use Laplace transforms to show this. And also notice that for our generalized I of t function, we had integral from 0 to infinity of sine of tx over x, which was also a constant pi over 2. I mean, in our last video, we had taken a similar approach of Laplace transforms, and we ended up with an expression of t when we took the inverse Laplace transform. And then we plug t equals 1 in that case too, like we should have in this case. But now notice in this case there is no t, so this means for every t I of t is always going to be pi over 2. So that's why, remember, I said that if we have integral from 0 to infinity of sine of any constant a times x over x dx, that will always equal pi over 2. That's because of this fact, which is perfectly reflected above in the I of t function. So it looks like we actually found out the value of two integrals in a sense. This method of Laplace transforms is really powerful. So that's it for this video, guys. I really hope you enjoyed this as much as I did. Please like, share and subscribe to my channel. Recommend me to your friends. And stay home, stay safe, have a nice day. Peace out.